To one and all. So, on behalf of our organizing team, we welcome you all for the 6 days FDP program on advanced polymer composites for aerospace and mechanical application. So, in today's session, we have Dr. Ananthakumar sir. He is a scientist. So, it's a pleasure to invite our the speaker, Dr. Ananthakumar Ramdas, currently serving as a scientist and group leader at the CIPET, Advanced Research School for Technology and Product Simulation under the Government of India. So, Dr. Ananthakumar holds a 2 PhD, one in physics from Bharathasan University and another in mechanical engineering from Seoul National University, South Korea, where he also received a best doctoral thesis award. His core research areas include energy storage system, hybrid nanostructured material, supercapacitor, surface engineering, and additive manufacturing. His work is known for bridging material science and real-world energy applications, especially in designing next-generation flexible, lightweight, sustainable devices. Over the years, he has been awarded several prestigious fellowships, such as Alexander von Humboldt Fellowship from Germany and a BK21 Plus postdoctoral fellowship in South Korea. He has successfully led and mentored numerous national and international research projects, many funded by DST, UGC, CSCR, and DAT, etc. Ananthakumar has published over 100 high-impact research papers, holds a patent, authored chapters, and is recognized consistently among top of scientists in the world by Stanford Institute. It's not only a leading researcher, but also a passionate mentor, having supervised multiple PhDs, postgraduate projects, and has actively organized national, international workshops and symposium. We are really honored to have him with us today. Let's warmly welcome Ramdas sir to enlighten us with this experience. Please.
Thank you for your introduction. And thank you, Dr. Shasmita Madam, to invite me to deliver a talk in this section, Faculty Development Program. So can I start my program, Madam?
Yes, sir.
Yes, thank you.
Please, sir. Thank you. Thank you for accepting our request.
Thank you, ma'am. Again, so good evening to all. Today I'm going to discuss about the functional 3D printing polymer composite filaments for diverse applications. So everyone knows that today most of the technology is overcoming by additive manufacturing compared to the conventional traditional manufacturing technologies. In these various additive manufacturing techniques are there. In that particularly today I'm going to discuss about the filament fabrication. That means fused filament fabrication or fused deposition modeling. So in this printer, initially the people have used for printing many polymer materials, not starting from the PLA, ABS, and PEEK, those kind of things. So later those material only restricted with their limited application, and they can't move towards other application. In this case, we have slowly they started with the adding of the fillers or carbon fillers in terms of carbon fibers. So that also mostly focusing only for the mechanical enhancement or it is restricted to the particular application. But still these things want to go for the wide application. People started to use for the various researches happen to the functionalizing filament with the various material depends upon the application that will be functionalized. That means added the fillers and make a filament. That filament can be printed by using the 3D printing filament. That means filament 3D printing filament, FDM based printers. So today's my topic is mainly based on the introduction about the various additive manufacturing techniques, followed by the materials. What are the materials they have used for the 3D printing, and then in particularly FDM based printer materials, processing and application, and finally what is the benefits and drawbacks and limitations available for this printer, and what I can conclude overall the summaries. So as I told, the additive manufacturing is the opposite to the subtractive manufacturing. So such as CNC, we can able to have a one block. From that block, we can removing the materials. Their wastage of the material is more. So however, when we are coming to the additive manufacturing, it's a layer by layer technique. So the material wastage will be less. So that's why the additive manufacturing is the opposite to the subtractive manufacturing, which was used widely in past, involving the gradual removal of layers from the solid block of any material, either be a wood or metal, to form an object. So as I said, the things initially one block will be there or wood will be there. By removing those parts, we can able to get one kind of object what we need the things. But however, in additive manufacturing, it's another way. So it's a name of indicated, it's a layer by layer deposition in a specific material to form a 3D shape or structure. That means layer by depends upon the total layer that based on the design, it will take the volume. Based on the volume, it automatically it will make a slice code by using the softwares, and then the slice based on the number of slice, it may be printed by the layer by layer deposition. So in this case, the wastage will be less. That's why additive manufacturing is the same name indicates the layer by layer deposition of a specific material to form a 3D shape or structure. This technique can be employed in the form of either ceramic, metal, liquid, or in the form of resin. So anything we can able to print. So we have to decide, first we have to decide which application we are going to implement that one. So based on the application, we have to decide which printer we want to go, and based on the printer, which material can be possible to things. Then accordingly, we can able to select the things. So that's why the material is versatile material. These days, many materials we can able to implement in this additive manufacturing. So that's such as the liquid also is possible, metal also is possible, ceramic also is possible. If you want to make any composite based thing, that is also can possible the things. But the printer should be the open source printer. If it is a printer is restricted with only the material they procured from the same from the company, those things only means we can't able to do out the things. But however, most of the printer nowadays is coming in the open source printer. There we can able to print whatever our own material we can able to use, and we can able to print whatever the whatever the design we are having the things. For in this case, additive manufacturing, we should know the designing knowledge. We should have the thinking capability of which design we want. If we know that design, which design we want, that design has to be designed by using the CAD/CAM software. Once the software has been designed by using the CAD/CAM software, then we can able to convert it into the machine code. Then that can be printed. That means that can be converted into the machine. That means additive manufacturing file, STL file. Then that can be going for the printing. So then we can able to get the product based on the printer. So here another advantage is complex shapes and design elements can be easily cured of the material using additive manufacturing techniques. If you are thinking about the CNC process, some of the complex shapes or some of the porous structure we can't unable to do it that much perfectly, or it will take long time to do the things. However, in this case, it's a layer by layer process. So that here layer by layer process based on the technique, based on the source will be vary. So accordingly, we can able to get the even complex shapes and porous structure and fine tuned structure also we can able to get it from these things. So that is the advantage of additive manufacturing techniques. So as I told initially, there is almost zero wastage of the raw material in additive manufacturing techniques compared to the traditional manufacturing. In traditional manufacturing, we are removing the material. So that's why whatever the material has been removed, those things can be wasted. But however, in additive manufacturing, we are adding the layer. That means layer by layer we are adding. So in this case, the material wastage is less. That's why it's almost zero wastage things. And also a narrow range of materials can be employed for the process, which can be relatively low melting points. So this is the overall view of the subtractive technique and the additive manufacturing techniques. From this, you can easily identify the things. This is a one block will be there. With these blocks, we are removing the materials. So this is a top-down approach. So when we are removing the materials, finally we are getting the part. But however, whatever the removed thing is high wastage. So if you come to the another part, so additive manufacturing techniques. So we are adding the layer by layer and we are getting the final product. So that's why it's we can call as a bottom-up approach, and the wastage will be less. So this is mostly 3D printing is a process converting a three-dimensional CAD model into the physical object. So it can be possible to go for the any complex geometry the things. One thing is we have to design it accurately, then design can be implemented by the choosing of the printers, and based on the resolution of the printer we can able to get the resolution of the product also the things. So from this right hand side we can able to see the conventional method. We can able to go for the parallel plate architecture. If you're going for the 3D printing structure, 3D printing method, we can able to go for the 3D printing structure. In the 3D printing structures also we can able to prepare the things with the whether fully, that means a fully empty 0% or infiltration with the 10% or 20% we can able to increase. Based on that we can able to increase the weight of the product, or we can able to the quality or the mechanical stability and the strength. Those kind of things also we can vary with the infiltration percentage, as well as the what kind of pattern we are making. Accordingly the property can be changeable the things. So this is a CAD model and this is a printed prototype. The first 3D printing has been that means developed by Charles Hull in 1986. It's known as a stereolithography. It is a process just like a photolithography by using the mask pattern. We are using the photopolymer things, photopolymer. Once we are after we are making the lithography pattern, then we can able to be exposed to the light. We can able to get the pattern. Then we can remove the photoresist. We can able to get the final pattern structures. So similar way only here they have designed the design has been designed by the CAD/CAM software that can be converted into the stereolithography file that will be inputted into the 3D printer. Whatever the design we have designed, those things can be printed by using the layer by layer. Here in this stereolithography, they have used as a resin because they have used a photoresin. With the photoresins, by using the UV light or UV laser, then we can able to cure the part and we can able to get the final part. So this is the same thing. This material is be there subtractive and 3D object we are getting this much of the wastage we are getting. However, in case of material will be there additive manufacturing and 3D object and wastage will be less. This is the overall concept of the additive manufacturing things. So how it is started from the 3D printing means it's initially started from the 1947, but that time nobody is ready to accept the things. But first one 1980 only Dr. Kodama of Japan founded the first rapid prototyping system. But followed by the things in 1986 only Charles Culls printed a furniture part using a photosensitive layer resin that can be printed by layer by layer. They have named it as a stereolithography. So followed by this, Carl Deckard created a selective laser sintering. So it's another form of printer. In stereolithography, mostly they have used a resin-based system. When you are coming to the 1987 selective laser sintering, here we can able to use a powder. It can be a powder, can be a ceramic or polymer. Only the source is here is laser. That means the laser will be sintered the material to fuse together and make a part the things. Initially the curing agent will be using by using the UV light or UV laser, then we can able to cure the material in 19, that means stereolithography. In this case we are using a sintering the materials. Then followed by the Charles Culls in 1988, that means 3D System Corporation released the world first commercial printer, that is SLA1 1988. Followed by the Scott and Lisa Crump filed a patent for a fused deposition modeling FDM. So this is the most common printer nowadays. So everywhere we can able to get the very cheapest one. The things we can able to get 15,000 also 20,000 also less than 50,000. We can get a good printer also. Things in future every home we will have this kind of FDM based system because there's low cost, and if any issues in our home, if something is a switch based problem or any part can be damaged or it cannot be get the problem, that means obstacle parts, those things can be printed by our home itself. The things because many things can be digital system have, it will have the designs, so those design can be freely available or cost we can pay from the designs, those can be given input to the FDM printer. We can able to print the things because it's a polymer based printer, cheapest one and less cost, and many things can be printed by using things. So that's what FDM every home we can have in future, one printer fused deposition modeling. So here the material is mostly polymer based system or composite material also. These days we can able to implement the things, whatever the problem is happening, whatever the any part is damaged, those part can no need to go to the shops and get the things, or if not unable to find, we don't want to wait for a long time. We can get the design and we can able to print by ourselves, we can replace the things. So that's the advantage of this technique, the things. And followed by 1989, Wake Forest Institute of Regenerative Medicine grow the first 3D printer urinary bladder. And then followed by the 2005 also self-replicating manufacturing machine was created by Dr. Arden Boyer in the Worldwide Recap project. And followed by the many things are come out, and finally nowadays people are without man people have started to print the many building also. That means constructing building, schools, homes, office, this can be slowly started with the things, and they have printed and it's showing the good performance compared to the normal building construction. So like this it's evolving the things starting from the SLA. Nowadays many printers has came out as per the standard. This can be classified into 7 types, and one by one we can able to see the things. So why this 3D printing is, one is efficiency, innovation and customization, localization, sustainability and future technology. In terms of efficient innovation, what it can be means it's eliminate the wastes and cost will be reduced and foster innovation design. So if we have design, we can able to print the things, and whatever the design we want, that is also enabled. That enables personalized product and strengthen the local supply chain. And it can also be a sustainability, support eco-friendly practices and democratizes manufacturing process. And also we can able to go for the AI, then CAL, AI and the space exploration process also is possible by using like this. Various advantages is there when we are going for the 3D printing application. So how we can able to print the full processing condition is coming from the starting from the what are the step-by-step process means. First we have to go for the design. As I told, the designing is the must. If whatever we want, whatever we are thinking, that has been designed by using the CAD software. Any kind of CAD software, either SolidWorks, AutoCAD, CATIA or NH, so those kind of softwares we can use and we can able to design the things. So once this can be designed, the first step, then we have to go into the 3D models. The design 3D models are converted into stereolithographic file format. It's a 3D printing file format. Those file format has been used, input has to be given to the 3D printing. So the data from the STL file format is sliced into G codes, and then the design has been printed. So depends upon the volume, that can be the number of slices can be vary, and we can number of layer thickness, and it can be automatically this number of slices can be detected. Accordingly, it can be printed the things. Once the part has been 3D printer has been completed, then we have to go for the post processing. So most of the 3D printers, we have to go for the post processing, because the 3D printing process sometimes it may be the surface not be good, and the dimension will sometimes the problem will be there, shrinkage will be there, or bigger dimension will be there, or any kind of pores will be there, and that means the look will not be good. So for that case, we have to go for the post processing things. So during the post processing things only, we can able to improve the surface finish and the property of the printed parts. Then we can able to go for the finally the 3D printed parts will be ready to go for the commercialization. So during post processing things, so depends upon the printer, we have to decide which kind of post processing things, whether that is mechanical or chemical or machining things or any other things. Post processing is record, those will be decided based on the application, based on the printer we have to decide, and based on the material we can decide the things which kind of post processing record to make a product and attractive, and to go for the sellers to in the form of selling to the people. So what are the advantage of when we are going for the 3D printing is, one is flexible design, and it is a geometrical freedom. It can be rapid prototyping, and also material waste is less, and short supply chain. So like this, many advantages there when we are moving towards the additive manufacturing. So this is the one once the G code has been done, and it can be making a slice. So this is a layer by layer part, and finally we can able to get the close, that means full product. So STL format, G code conversion, and layer by layer printing. Finally we can able to get the object. This is the full process of the 3D printing. So in this, what are the 3D printing family? What are the 3D printing, various 3D printings are there, additive manufacturing techniques are there. So the families, as I told, 7 families are there. One will be the material extrusion. So that means the material will be extruded, and we can able to get the things. So in this first one is material extrusion. It is a solid filament. Either it can be the filament can be a polymer or metal. So it can be a composite filament or pristine filaments. So both the things can be possible to do that. In this material extrusion, if you are considering the polymer, it can be we have to select the fused deposition modeling. If it is a metal, we have to go for the selective laser melting or direct energy deposition or electron beam deposition. So this kind of techniques we have to go for the material extrusion. So and the next one is powder bed fusion. The powder bed fusion is mainly based on the powder based material. That means the powder will be there, the powder will be spread over these things, and then we can able to pass the any kind of selective laser. That means selective laser melting or selective laser sintering. So these things can be by using laser, we can able to melt or we can sinter the things. So that process we can able to go for the powder bed fusion. So and then binder jetting printer, it can also one kind of the powder will be there. So over that powder, the binder will be spreaded over the material, and that can be that the binder can be fused together after making the green part. Then in this case we have to go for the post processing things. During the post processing things only, that can be sintered, the binder will be removed, we can able to get the final cured and sintered part the things. So that's the things for binder jetting. So it's a post processing must for the binder jetting. Then VAT polymerization. In this VAT polymerization, as I said initially, it's a one kind of photoresist we have to use. Either in for VAT polymerization, 2 type of things will be there. One is stereolithography, another one is a DLP, direct light deposition. Sorry, for DLP, another method will be there. So next one will be the sheet lamination things. Sheet lamination is another kind of additive manufacturing. In that case, one will be there, sheet will be there. After that, another sheet will be pressed with some glue, and then another sheet will be pressed with the glue. So like this, layer by layer with means. So either this can be possible to done with either 2 ways. Well, after addition of all the layer, we can use by laser, we can able to cut, or layer by layer. Once layer has been fused, then we can pass the layer and we can remove the layer. So like this, so both the ways we can able to get the 3D project. And then material jetting. So just like an inject printer also, that is inject printer, or in the form of the liquid that it is consists of the material, those can be inject printed, and we can able to get the things that is coming under material jetting. Or another way we can able to material jetting fusion, multi-jet fusion also we can able to see the things. And finally is the direct energy deposition. It's a direct energy deposition, just like a melting. So here also that thing, same thing will happen in the things. So like this, various families are there. These families are accredited by the ASTM 52900 15 or formally ASTM F2792. These are the various families of the additive manufacturing. Again, these additive manufacturing families can be, we can able to distinguish the liquid, solid and powder. In case of liquid, as I told, two things will be there. One will be molten and polymerization. In case of molten, mostly plastic based material, that is material extrusion and coming under the various material in terms of the polymer as well as the metal is possible. And then polymerization, liquid based synthesis will be bad polymerization and material jetting will be there. And solid based will be a bonded object sheet lamination. On powder based one is melting and binding. So melt in case powder bed fusion will come and direct energy deposition will be there. In case of binding, only binder jetting will be there. Again, still if you want to explain the things families, we can able to go for the solid. In case of solid, sheet, it can be joining. So joining can be taken by two way. One is laminated object manufacturing or ultrasound additive manufacturing. If you are coming into the filament, three melting will be there. Melting can be three. One will be the material extrusion, another one will be the powder, that means powder bed fusion, another one is direct energy deposition, DED, direct energy deposition. In case of material extrusion, that can be divided into two. One will be the fused deposition modeling or fused filament fabrication. In case of powder bed fusion, again three things will be there. One will be the selective laser sintering, another one will electron beam welding, another one will be direct metal laser sintering. So this is another one. So it's coming to the DED, direct energy deposition. Again, three types we can divide it. One will be the laser imaging, net shaping, and electron beam, and then plasma arc melting the things. Similarly, next, if you are coming to the powder bed, one will be the binding. In case of binder jetting, only one technology is there, binder jetting, three-dimensional inject technology, and then multi-jet fusion, MJ, the inject technology, as well as direct ink writing. That is also we can able to say. So then, if you are coming to the liquid, it's a polymerization, bad polymerization, we can say in this case, as I told, stereolithography. Another one is digital light processing, that is DLP. So one will be in the stereolithography, the part can be going, and that means once printed, the part will go down, and the next layer will come. In the digital light processing, the light will be processed in the form of downward things, and it will go upstairs the things. So like this, these are the various types of 3D printings are there. Today, mostly we are going to discuss about the filament based system, particularly for polymer systems compared to the other metal or powder based systems. So as I discussed the things, what is material extrusion means? Material is ejected through a heated nozzle, facilitating layer by layer deposition. In terms of powder bed diffusion, utilizes a laser or electron beam. We can use either laser or electron beam to melt or bind the powder materials together. In this case, we can melt or bind by using the laser or electron beam or fusing the things. And the next one is binder jetting. Here we have to use for the liquid binding agent and the powder layer, which is followed by the force processing to solidify the printed part. Initially, the binder layer, once binding agent has been applied, we can able to get the green part. Followed by the green part, we have to keep for the post processing centering. Then we can able to get the final solidified part. And next one is material jetting. The 3D parts are printed as the material gets jetted into its built area, and it's followed by the UV curing or hardening. And then direct energy deposition is also one kind of metal based system, and deposition of the material by the energy from the electron beam or laser onto the surface of the existing part, so that it adhered directly. Well, if any part is a damage, so directly we have to go for the deposition of the some of the damaged things, and that is also possible by using the direct energy deposition. And then bad polymerization is another one through a selective curing liquid target. That's a light activation. So stereolithography or direct laser printing, or that means digital light processing. So like that also we can able to say. And then finally, sheet lamination. Sheets of the materials are stacked, laminated together to form an object. The laminated can be adhesive, chemical welding, or bracing. So many ways we can attach the layer. One layer material sheet will be there. Another sheet will be attached with either adhesive or chemical or welding or bracing. So after that compression, we can do both can be joined together with the heated. Then after that, we can able to pass the laser to cut it exactly whatever the design we need the things. So next layer we can do the same thing and cut it the things. So that's why two ways we can able to do the sheet lamination. One, we can laminate all the sheet. Finally, we can pass the laser and we can remove, or the layer by once the layer is attached, suddenly next followed by we can able to pass the laser. We can make a prototype. So like this, these are the various techniques we can able to see the things. And in this today, we, as I told initially, we are going to discuss about the fused deposition modeling. It's a fused deposition modeling printing is the original game changer, and the dot additive manufacturing from factories to the desktop worldwide. It is developed by the studies in late 1980s. FDM works precisely melting and depositing the thermoplastic filament layer by layer to transform the digital design into the physical object with a remarkable a remarkable accuracy. So unlike traditional subtractive manufacturing, FDM builds parts additively, minimizing the waste while enabling the complex geometry, functional prototypes, and even end use of the parts. And from the rapid prototyping engineering labs, customized medical devices, and many materials can be possible to use PLA, ABS, nylon, and high performance polymer, just like Altum, and accessibility to have the many backbone of the 3D printing. However, initially the strategy started in 1980 or 1980. Initially, we have the things that, I mean, what are the material, what are the filament we have procured from the strategies only. We can't able to use the other material to give the input as the things. But however, we can able to use the other material, but we have to find in the property, or we have to break the software, we have to remove the chip based system. Then only we can able to use. Otherwise, it is difficult the things. But nowadays, the people are having the, as I told you initially itself, it's an open source. That means we can use any kind of material that, but the property of the property should be matched with the filament property. Then only those filaments can be, the filament can be used for this printing of the things. So whether that means if you are considering the PLA, the filament is like the printer filament record 1.5 mm dia means it should have the 1.5 mm dia of the full things. Otherwise, the dia should be uniform throughout the things. Otherwise, we can't able to print the things. If the dia is varying in between the, if while printing, that can be printed out. That means it can be breaked. So those kind of issues will come. So the whatever the properties record, the flowable property, viscosity, everything we have to make. That means the data set has to be matched with the commercial database. Then only we can able to use our own commercial. That means own prepare the filaments. So that then we can able to use the things. So that can be based on the filament can be fabricated based on the application. Which application, whether this aerospace means what are the properties required for the aerospace. Accordingly, we have to design the material. Accordingly, we have to use the filler material, and we have to make a composite filament or functional filament. Then that functionalized filament should be printable by using the various printers, just like a filament fabrication or fused deposition, fused triple F or fused deposition modeling, any kind of the printer. So whether this can be used for this aerospace education or garage or FDM continues to push the boundaries innovation, proving that the future is not just manufactured or it is printed. So how it is rising the global 3D printing filament, from that you can able to see almost 19.8% will grow after 2033. Nowadays, now 2025, how much the material type, the billion USD million is, it's showing the 1374. In the projected one, if you see 19.8% is increased, it is almost a 5831 the things. So like this, many advantages are there in this case of the introducing that means the 3D printing filament market is rising gradually. Things we can be still be need based on the application. We have to go for the new kind of filaments that should be implemented for the application. The problem of the fused filament fabrication filament is always we record the polymer the things, because thermoplastic based polymer, so that should have the filament. And also when we are going for the polymer based system, if we are loading with any other fillers, whether that is metal or ceramic or any kind of other fillers, the filler percentage when we are increasing, the filament get brittle. So that times we can't able to print the things. So that's why we have to always optimize the things, the polymer percentage, filler percentage, and plasticizer or any kind of additives. However, the people can't move the higher percentage of the fillers because of the brittleness. The printable property will not work out for the things. So that is the drawback. Even though we can able to go for the small amount of fillers, but large amount of fillers that cannot be suitable for the wherever the application. If the some places for a polymer should be lowest and active material should be high, in this case this kind of printer will not be suitable. So that's why the less filler percentage with the high polymer content is feasible, and those applications we can select with this FDM based printer. And in the case of fused deposition modeling, this is the printing the schematic diagram. This the filament has been initially prepared by using the filament extruder, whether that can be a single screw extruder or twin screw extruder. Once the extruder, once we are getting the filament, that filament has been inputted into the filament extruder. So it is the most commonly used method for 3D printing of these days. FDM is used for the production of 3D prototypes and small scale and product as well as thermostatic material, just like a polylactic acid is used as a process of the core material. PLA we can able to use, ABS we can able to use, PEEK we can able to use, nylon we can able to use, TPU with thermoplastic thermoplastic, that means TPU we can use, or polycarbonate we can use, PET also we can able to use. So we can design various thermoplastic polymers, as well as these polymers can be functionalized with the less fillers as well as the high amount of fillers, also moderate fillers also we can able to use. Once we can make it a filament, that filament has been fed into this system. So by using the driving motor, the filament will be go down to the system to the nozzle. So here will be the heating temperature, heating portion will be there. In this heating portion, this will be molten. It will come due to the heating. It will be converted into the molten paste. Those molten state will can be gone to the nozzle. From the nozzle, the things can be printed based on the nozzle tip and nozzle dia, nozzle resolution. The printing of the parts can be varied. If the nozzle tip and nozzle size will be bigger, we will get the layer thickness of the things. That means each the flowable liquid will be high, then we can able to get a thicker layer thickness. In this case, we can't able to get the good mechanically stable things. So that's why the resolution of the nozzle will be play a major role to get the highly mechanically strong product the things. So that's what we have to design the things. That means this will play a major role. We have to decide when we are procuring the printer. We have to consider about the nozzle as well as the high temperature nozzle. So then only we can able to go for the high temperature material also the things. So here while printing, it can be extruded moving things happen between the x-axis or y-axis or z-axis also is possible. So extruder, this is the total extruder, and this is the molten paste chamber and the nozzle tip. So once the 3D object is printed in layer by layers by heating the thermoplastic materials and extruding into the layer by extruding the nozzle, the liquefier heat along with the extrusion nozzle moves x and y coordinates according to the instruction already feed into the printer depending on the design of the 3D object. Each layer, when it is formed, consolidated with the layer beneath, it is hardened by the time. The fused deposition model is quick and produces the 3D product with the stick of the finishing. How this together it is happening is one layer is forming, so another layer is forming before next layer. Before that, it may the temperature will maybe vary. So but however due to that, that's what we have to keep the always the chamber temperature has to maintain, as well as the base temperature has to maintain, and the extruder temperature also we have to consider. We have to make it according. We have to optimize the things to make it that both the first layer and second layer to be fused and make it into the prototype. So how it is happening means you can able to see the things of the part from this formation of the layer bonding in the FDM product. You can see first layer will be there and second layer will be here. The surface contact or diffusion and neck growth will be there, and finally inter diffusion. So like this various stages will be there. Once the inter diffusion is happening, then the product will be packed clearly the things. So FDM parts, once the filament is deposited by layer, the polymer layers start diffusing and get the bonded. Ineffective bonding develop the pores that leads to increase the part integrated homogeneity. If it is not making properly bonding properly, we can able to get the, that means pores will be there, our surface structure will be different, our surface roughness will be there. Then we can able to get the inhomogeneity. Then we can get only inhomogeneity particle prototype product, as well as the surface finish will not be there. Then we can able to go there. That's what while printing the part has to be, diffusion has to be happen, then only we can able to get the good part without pore structures. FDM parts begin forming a neck growth with a pre-deposited layer. So it's the first layer, and then second layer surface contact will be there, and then it will happen the diffusion neck growth, and finally inter diffusion happening, and the part will be get more strong. The bonding of the layer can be modified controlling the parameters of the FDM process. The high temperature of the nozzle to increase the bonding capacity of the layer. So like this, the formation is happening in the FDM molding part formation of the layer one by one. So first layer and second layer, and then next layer. So until how many layers like happening. So like this, layer by layer, the process will be happen. Finally, we can able to get the more good and viable part. So when we are going for the next one, so this is the same thing, the filament and driving motor and extruder, we can able to get the things. So the filament dia should be the 1.5 to 3 mm. Depend upon the nozzle size, we can able to change the things. And starting from the generally, commonly people will use 1.75 mm as a filament dia will be suitable for the most common filament dia. And what are the materials we can able to use means we can able to use PLA, ABS, and PA. That means polylactic acid, and then nylon we can use, and then similarly for polymer composite also we can able to use. Polymer is filled with the fibrous, and what is the drawback is only limited material, only thermoplastic we can able to use. But benefits is it is a rapid prototyping, cost effective, lightweight parts, and many things. It is advantages. That's what I told you, the things we can able to keep in our home, and we can able to print many ways. The additive manufacturing things can be able to use. Either it can be education, it can be agriculture, and it can be aerospace, it can be military, and also healthcare. So like this various application we can able to use this fused deposition modeling printed parts. And in this case also, whether printed parts can be happen for different things also. Either single print, that means The pure pristine filaments also we can able to print, or pristine filaments with the reinforced with the materials. That means single filament consists of the matrix as well as a reinforced material that can be printed by that can be possible to print. And another way also, the reinforced material will be separate and matrix material will be separate, but print head will be single and part can be printed. And then another way is the two nozzles. One nozzle will have the matrix material, another nozzle will have a reinforced material. Like this also print a possible to print. And these days people have started to use multi-material, because single material, another material, we have to fit the things at a time. We can't able to print the things. What are the old technique? But however, in the present days, we can able to go for the multi-material nozzle. That means one material we can use the sacrifice template material things. Another one is the active material. If you want to bind with the different materials based on the programming, we can able to go layer by layer, various material is possible, and to with the various material and various thickness. So like this, many things we can able to change the parameter things, we can able to get the final product. So that's the advantage of when we are going for the multi-material oppositions. So one fused filament fabrication reinforced with the composite filament, first one, and second one is combined filament and fiber in a single nozzle, and then combined filament fiber with the two independent nozzles. And many nozzle also we can able to add based on the application. We can able to decide how many materials we have to add. Accordingly, the cost of the equipment also will vary, and the cost of the equipment also vary, and the nozzle also vary, and temperature also, if you want various temperature of the bed, that is also is possible. And each material I want to use different nozzle, that is also is possible. So like this, many ways we can able to use this FDM based printers. And then this is the same thing happening for the single head printed the things, and double head that is different material in single nozzle, and different nozzle also dual head method, and in the single nozzle with 12 materials. So many things we can able to print the things. So what are the parameters we have to consider while printing this kind of filament based filament fused deposition modeling? Means we have to consider about the slicing parameter. First, before printing, we have to consider about the slicing parameter. That means layer thickness. We have to think depends upon the layer thickness. That means if the layer thickness will be high, the visible line we can able to see. That means more rough surface we will get the things, and attachment of the binder first layer and the second layer, it will not be good. So the mechanical strength will not be good. So that's what the layer thickness, a minimum layer thickness will be give the higher accuracy as well as the surface finish, and mechanically also strong. So that's what we have to think. A layer thickness will play a major role, and flow rate. So how much the flow rate we have to optimize this thing. That means the temperature, melting temperature and molten state, how much temperature has to be given, that we have to fix the things, flow rate. And deposition speed, how fast the printing has to be happen, whether the printing speed, whether the quality will be good or printing slow or moderate speed, that also we have to optimize these things. And infill percentage, as I told, infill percentage can be a 0% or 50%, 10% or 30%, depends upon if you want to make a lightweight material, we can able to reduce the infiltration of the things accordingly things. If you want it with infiltration with a good mechanical property, in that case we have to design the various infiltration designs, then accordingly the strength also will increase with a lesser filling percentage. So like this, we have to design the things initially itself, slicing parameter and raster angle. So how it is has to be printed, raster pattern and concord width, and what is the air gap and nozzle diameter on top and bottom width. So everything we have to consider initially itself, then only we can able to get the good things. And then next one is building orientation. How we can able to print it. The part can be printed directly and angle, or that means horizontally we can keep, vertically we can keep, or lateral we can keep, or one or other we can keep. So like this we can keep it. But advantage also will be there, disadvantage is there. So if it is a vertical, horizontal, lateral will be there. If lateral is there, we need to keep the support structure. When we are keeping support structure, we have to remove those support structure. When we are removing the support structure, those places can be rough surface will be there. Again, we have to go for the post processing thing. The smoothness will not be there. So and depends upon the part. Some part we can't able to give the vertical. Some part we have to give the vertical. Some part horizontal. Some part lateral. So it depends upon the printing orientation also. The surface finish will be vary, and the surface quality also will vary. So accordingly, we have to depends upon that. We have to decide which orientation has to be there. And temperature condition. So what will be the temperature? Bed temperature. So where the printing will be happen, those things bottom will be considered as a bed. So those bed platform, whether that can be a bed temperature has to be optimized. So on the extrusion temperature, that means the molten state, the material has to be happen. That's why extrusion temperature has to be matched with that one. And environmental chamber, the chamber temperature. Those all the things will play a major role to get a good product. The things. So as I told initially, the first one will be the 3D modeling and conversion of the model into the STL file, and then slicing of the number of files based on the volume of the materials, and then 3D printing, and finally post-processing, sorry, it's a final product, and then we have to go for the post-processing. Once we are doing the post-processing, we can able to get the attract, that means good product. So in this, as I told you initially, the FDP process parameter. So what are the process parameter? We have to slicing, building orientation, and temperature. In this case, from this slicing parameter, first we have to consider about the air gap, the spacing between the adjacent raster, which can be a which can be negative overlap or zero touching or positive speed. Negative gaps improve the density but increase the build time, while positive gaps reducing build time but weaken the tensors. From this we can able to see what is concord width. So this is a final outer line of the concord width, number of concord width. We have to decide the things on concord air gap and air gap between the each layer. That means the air gap between the layers. That means whatever the how we are making the pattern. So infiltration accordingly these things will be the air gap and raster width. So each layer that raster width and raster how angle, how it is printing. So this is the angle of the printing. So how it is the printing and number of contour is happening and perimeter diagram. So all the things we have to decide when we have to do this. Based on this, the part quality can be varied. So we have to decide the things. That means this parameter should be optimized things. So that's what FDM parameters majorly play a major role. Several attempts were made to enhance the FDM process parameters that have a big impact on the strength of the build parameters. Many researchers analyzed various controllable parameters to attain desirable properties of the parts, and more of them agree on the identical number of the critical parameters. Generally, 3 parameters only: slicing parameter, building orientation, and temperature orientation. Temperature condition. In the slicing parameters only, first one will be air gap. So this air gap will play a major role. And next one is printing speed. So when the speed is high, we can able to get the enhanced tensile strength due to the better laying bonding. But may compromise precision. So while printing, it can be the precision will not be there. So that's why we have to optimize the printing speed also things. While printing fast, that time it may not be proper the things that can be overlap the things. So those things has to be avoided when we are going for the optimizing printing speed. And raster orientation, the angle of deposited layer related to the build platform axis, it moderately affects the mechanical property by determining the filament alignment. And raster width also, the thickness of the deposited rasters, wider the rasters improve the fluctuation but reduce the tension due to the weaker interlying bonding. And then initially I told you build orientation, whether horizontal or vertical or a lateral structure. So accordingly the surface finish will be vary. So that's why based on this axis significantly impact the surface finish and mechanical properties based on the layer and directions. And then temperature condition also, nozzle heating temperature critical for material extrusion. So high temperature improves the layer fusion and strength but require precise control to avoid the defects. When you're going for the high temperature, they should not be melted more and it should not be flowable, it should not be liquid like the things. So that's why we have to optimize the temperature also. Based on the temperature, the nozzle via the molten metal has to be moved for the nozzle and it has to be printed. If you are giving high temperature, so first layer and next layer should be diffused properly, interdiffusion should be happen properly, then only the bonding will be good. If the bonding is not good, it will easily visible layer we can able to see. By the visible layer, it can be easily tearable the things. So those things can be avoided by using the laser thickness, optimizing layer thickness, less printing speed, and raster orientation and infiltration percentage. Based on that, we can able to get the better, that means enhanced property of the prototypes products. So same things only happen to this. What is the air gap and what is the raster angle and raster width and what is the layer thickness. So layer thickness is the layer, first layer of the thickness, and next layer what will be the things. And infill density is the 10%, 0%, 10%, 25%, 50%, or 80%. You can see from this what is that infill is a percentage and what are the infill pattern also, how it is look like. The pattern can be vary. So based on the infill pattern, the quality of the prototype property also will vary the things. So these are the various pattern like structures. You can see the things. So triangle like infiltrate pattern and grid like structure and cubic like structure and rectilinear structure and concentric structure, honeycomb will be there, and rectangular, octet, and big gill. So like this various structure of the infiltration structure also we can give to the things. So it's not mandatory to fill everything the things. Either we can able to go for the 0% also is possible, 10%, 20% also is possible, hollow also we can able to make the things. That's the advantage of this additive manufacturing techniques. So based on this infiltration percentage, the property will be vary. Mainly the property of the mechanical strength of the property will be vary based on this one. And also the lightweight or proper weight of the material also will be increased. If it is less percentage of the less percentage of the material infiltration, then we can able to get the lightweight material. When we are adding the more material, accordingly the weight of the material will be increased, and the property also is, that means that sometimes it may be go for the breakable, that means breaking that means brittleness is also is possible, then it may reduce the mechanical property also the things. So accordingly so we have to optimize the things, what kind of infiltrate percentage is required, and what is the infiltrant pattern is also is required. So we have to decide, and we can able to print accordingly the things. So what are the factors affecting the FDM process? Means factors to be considered for while 3D printing is, one is STL file quality, we have to check it, and then process parameter, as I told the things previous slides, air gap, angle, layer thickness, influence, contour width, and environmental factor, temperature, oxygen can have humidity. So whenever the printing, before that we have to make a chamber has to be there is a temperature control, that means we have to optimize the temperature, chamber temperature, and then bed temperature, as well as the due to this oxygen content or humidity problem, before keeping the filament inside, we have to keep the filament into filament should be kept into the oven, so to remove the humidity or any oxygen content. After that, we're removing the that means outside atmosphere, whatever the impurities, then we can fit into the printer things. Similarly, for raw material filament quality, the filament quality raw material is varying, then we can't expect the same temperature of molten state will come. If it is any impurities there, addition of the any kind of fillers is there, then the temperature of the things will be vary. So we have to be sure about the quality of the filament, and what will be the density and water content available in the filament, or as well as if you are adding the more any kind of filler percentage is that, and automatically the melting temperature will be vary. So accordingly we have to again optimize the filament that means optimize the filament fabrication conditions. Apart from that, now filament machine also, if FDM machine also, we have to think about the things: nozzle temperature, bed temperature, chamber temperature, nozzle diameter, and machine calibration. All the things we have to do the things before starting the things. So first we have to go for the bed temperature and chamber temperature before printing the things, as well as the nozzle temperature. Once nozzle temperature is fitted, automatically the whatever the molten material will come out, and it will be printed over the bed. And nozzle diameter will be fixed based on the nozzle. If it is nozzle restoration is good, then we can able to get the fine deposition, we can able to get the higher good finish, as well as the highly strength material, the things. Machine calibration, if the machine is not calibrated properly, then the part cannot be filled. If that means printed unit, they printed properly, the defected part only we can able to get. That's why the machine calibration also is important, as well as the final, that means build part orientation, whether that can be X or Y or Z direction. This already discussed the FDM layer. This is the process things. And what are the advantages and disadvantages of FDM based things? It is a less material wastages, less expensive used materials, tools, and more cost effective than the other process, because it's a polymer based things. Polymer cost is less, and temperature also is less than 400 degrees sufficient, and less than 250 degrees also sufficient some of the material. So that's what we can able to print many things. We can able to polymer based ABS and PLA. This is user friendly material. Many prototypes can be printed by using the things with a less cost. And more expensive models uses a different material to remove the supports completely. Even cheap 3D printers have enough resolution for many applications. Therefore, FDM is currently most widely available additive manufacturing platform. What are the disadvantages? This means support leave marks, because whenever you are using the support structure, so when we are removing the support structure by peeling or by breaking, there will be a marks will be there. Those things can be removed by using sandblasting, or by using the chemical etching or wrapping, are limited to thermoplastic material. That means limited testing allowed for the thermoplastic materials. So these are some of the advantages are there. So another limitation is mechanical property of the manufactured part and specimen, limited range of available raw material for the selection. In fact, thermoplastic materials are only used as a FDM raw materials. So those are the materials can be used. After that materials, we have to add the fillers to make a new kind of functionalized filament that can be able to print with the things. So that's what various filament we can able to make by using the based on the application. Those material has been filled with the polymer materials, made a composite filament. Then we can able to print whatever the required prototypes are. After printing, so what are the surface finish has to be happened the things before surface, this means before post processing method or post processing. Two ways we can do things. Before post processing, as I told, we have to think about the layer thickness, orientation, temperature, and everything. We have to consider things. After printing, the part has been removed. Once the part has been taken, the part will come with the support structure. The support structure can be removed by player or by hand or when we are putting into the ultrasonication with some solvent or water soluble template, there's a template that can be removed. So if it is still after removing the part will be more rough surface, or the surface finish will not be good. So that's what we have to go for the post processing method. So if you are considering about the mechanical, many mechanical process will be there: sandblasting, abrasive milling, vibrating loading, hot curing machining, brushing, barrel tempering. Like this, many things we can go for the mechanical. And similarly for chemical means painting, we can do acetone dip and vapor smoothing and chemical etching or chemical polishing. Those things coming under the chemical. And thermal means laser surface processing or heating. That means we can keep for the sintering, and those kind of things also we can able to do. And small temperature we can able to go for the binding the material properly and increasing the physiochemical properties of the material. We can go for the thermal annealing, also thermal treatment we can able to go, or hybrid. So additive manufacturing process may join with the CNC accident milling, tuning, grinding. So why means we CNC milling means we have to go for accuracy. Once a prototype is taken, we have to see how it is look like, whether the dimension is correct or not. If the dimension is not correct, then we have to remove or we have to add. If you want to remove, we have to go for the CNC milling process. We can remove the process. If you want to go for the adding the material, we have to go for the any kind of small kind of deposition pattern process, or adding the infiltration process. So after that we have to remove this and go for the removing the polishing the things. Once we are polishing, then we can able to get this surface smooth finish. Once we are getting the surface smooth finish, then we can go for the painting. So painting based on the application, which kind of color, which kind of painting is required, accordingly we can go for the painting. So like this, many post processing methods are there. Based on the printing type, based on the application, we have to decide which post processing method is majorly required for those things. Once post processing is completed, the prototype is ready. So these are the methods for the surface finisher. So after in mechanical polishing, what we can able to, after printing the FDM component, a variety of post-processing processes are utilized to enhance the surface quality. The post-processing can be divided into mechanical, chemical, thermal, and hybrid. In mechanical post-polishing, the surface of FDM components is improved by either trimming, elevated surface profile, or compressing the surface peaks. However, finishing techniques commonly used for the metal can pose difficulties when applied to the ABS polymer due to the distinct material properties. Mass finishing relies on the abrasive forces to remove the excess material from edges and corners and resulting in a smoother surface. Alternatively, in polymer, most of the polymer people can go for the chemical-based finishing technique also, enhance the surface quality through chemical reaction alone, often without altering the component dimension. When we are going for the chemical based etching, either etching or removing or smoothing, so the material should not be removed, the dimension should not be removed. So we have to take care of the things, we have to take care of the conditions of the things. So then we can able to get the good quality of the materials. And then final thermal finishing method to use the controlled heat application to prevent both surface structure as well as the dimension accuracy. So these are the one of the method for the cold evaporation process. This is the paper tissue and acetone. So after that we can able to keep our material into the acetone vapor. Then after that we can able to get the finished product with a glossy look. We can able to get the things. The surface can be vaporized. That means the smooth and happen. We can able to get the make a two distinct instrument source power using the conventional CNC machine. Both exterior and interior surface can be melted. That means by vapor polishing we can able to get the good product, the good finished product. So this is the another form of hot vaporization process. Same thing for container will be there. In that container we can put it our material and then drying and then surface. You can see that then before polishing how the surface was there, after polishing is the same. This is a hot vaporization. So that's why solvent will be there. So material will be hanged and then the heat given the heat and by heat the hot plate. Then during the heating, the polishing things can be removed. After removing, we can able to get the surface finished product. So like this, many methods are there happen to get the better surface finished products. So how we can, these are the things for printing after post processing. So so how we can able to make a filaments. So those filaments has to be made. So development of functionalized filament, how we can able to make means we have to use for the extruder. That means extrusion is one of the process to make a filament. Extrusion is a process where molten polymer is forced through a die. So without filament also it can be possible to make a 3D printed parts. This is just as a fused filament fabrication. The pellet will be there. The pellet directly put into the hopper. Then hopper can be by hopper with the nozzle. It can be molten melted salt. The molten material will come and it can be printed. So like that also is possible. Or another way also is making a filament. So making a filament by using the extrusion. So that's what the extrusion is, a process where molten polymer is forced through a die and is used to produce the components of fixed cross section area of tube, pipes and wire and rod also it's possible. So this is extruder, conveyor belt, and measure and spooling. So later slides you can able to see clearly the things. So in this, extrusion is a huge high volume manufacturing possible, and the plastic material can be melted with the application of heat and extruded through a die based on the nozzle die nozzle, and we can able to vary the diameter of the filament, either starting from the 0.5 to 3 mm also we can able to see. So 1.75 is the standard diameter of the filament. So a cylindrical rotating screw is placed inside the barrel, which forces to molten our plastic material through a die. So this is the diagram of the things. Hopper will be there. Here the material will be fitted, and then this is the screw, and this screw consists of the many heaters. That each heater will play a major role, starting from the various temperature. Then we can able to get the molten material that will be come out from by the pressure. It will come out through a nozzle. It can be a tube or sheet or various structures can be possible. The things. So in the extrusion is a mechanical process in which certain materials are forced under pressure through a die opening to create a product to a desired shape, size, and structures. So extruder is a part of extrusion where the material is extruded in a liquid or semi-liquid form. And then commonly extruded materials are metal, polymer, ceramic, concrete, clay, and foodstuff. Product extruder generally called extrudates. And this is the same images. This is the same images. Hopper will be there, and first one will be the feed zone. Second one will be the here we can feed the material, and then second one melting, the melting zone. Here the material will be melted, and third zone will be the melting pump zone. Here the after melting, the melted material will be with the pressure, it will go out from the out through a die. So with the die we can able to get. So that's what we have to keep the temperature, various temperature, then we can able to get the things. In this hopper there is a single screw extruder is there, dual screw extruder is there. Depends upon the requirement, we have to decide whether that can be a single screw extruder or dual screw extruder. In if you are going for the precision material, just a single screw extruder is sufficient. We can able to use for only one single screw that can be rotated, and we can able to get the filament, whatever the thermoplastic filament. If we are going for the twin screw extruder, if you are going for the composite filament or the three various materials, we have to go for the twin screw extruder, because the advantage of this one is that can be a co-rotation is possible or counter rotation possible. With that the material can be mixed properly, mixing is properly, and we can able to get the fine tuned, that means a functionalized and composite uniformly distributed filament we can able to get. So that's the advantage of when we are going for the twin screw extruder, the things. So that's why both single screw as well as a twin screw, both they can able to use for the making the filament fabrication. So what are the major processes happening? How we can confirm the things means either polymer with any kind of fillers can be, that can be first we have to go for the mixing of the things. That means melt intercalation is happening. We can say the master batch. So during the batch process, both the material can be melted. That means a mixed, and we can able to get the some kind of polymer just like things. Those can be made into small pellets. So if it is whether it is a polymer or polymer with the metal or polymer with the ceramic or any other things that can be mixed, we can able to get the fibers. We can able to get the small kind of that means chips. Those can be made into small pellets. So those master batch pellets can be analyzed by SEM, TG, or DC, or any other studies also based on the requirement of the which one we want to confirm the things, whether physiochemical or thermal properties, that means structural property or composition property or mechanical properties. So based on that we have to decide which kind of analysis we have to confirm the things. Once this is confirmed, then we have to go for the extrusion. So this extrusion can be done by the things for the making a filament. So the extrusion we have to decide whether that is a single screw or twin screw. So based on that we can decide the extrusion, then the filament will come out. Once the filament will come out, again we have to go for the, before printing we have to go for the tensile testing, because mechanical property should be there. If the filament is it's not a flowable filament, it's a brittle filament, then it's not good. If the flowing is fast, that is also not good. So that's what the tensile property of the property should match with the Christian. That means wherever the printing requirement of the things, those things has to match. So accordingly we have to make the tensile, hardness, compression testing, mechanical, or if you are making a composite filament, the fillers has to be uniformly distributed throughout the filaments, as well as the filament percentage, how much percentage of filament is loaded, that should be there. How it is loaded, whether that is some places it is clamped and aggregated, or it is not, it is gap is there. If it is a gap is there while printing, what will happen? We can't able to get the functionalized filament, functionalized prototype. Sometimes what will happen, the temperature may be vary, it can be breakable things. So that's what we have to make a uniform throughout the distributed filament, then we can able to get things. Once the filament has been tested, then we have to go for the printer. So once the printer has been printed, the part has to be checked. First we have to check the dimension, then surface finish, then whatever the post processing is happening, then we can be able to go for the product final prototype the demonstration, or we can go for the selling purpose. So like this, various processes happening from starting from the functionalized filaments. That means first we have to go for the master batch. Then master batch has to be go for to the extruder. The filament can be fabricated. Then go to the 3D printer. Then printed parts can be evaluated. The things. So like this, various processes are happening for the making the functionalized filaments. So in this case, what is filament extrusion? As I told the things, filament extrusion is a process whereby a machine converts the raw plastic pellets into the filament wires. This can be at various steps, 5 steps majorly. The pellets has to be put into the bin. Then they select the desired setting based on the temperature, pressure which has to be there. Then the extrusion process is happening. Wait a few hours, then we can able to get the filament. So what is the advantage of filament? Means it's a rapid and combined with the different granules possible. So if it is not properly mixing, we can make a granules. Again, we can re-prepare the granules and we can add the additives. Again, we can able to get the throughout the filament. Then like this, many playing things we can able to make a filament fabrication to get a uniform and optimized filament things. So once the filament ready, we can able to go for the printing. This is the things for the single screw as well as the dual screw. The thing. This is a full setup of the things. Extruder, hot bath or cold bath. Both we can able to. So depends upon the material. Some material can be not suitable for the water. So those kind of things we can able to go for the air cooling also is possible. So both the bath things can be done. Then we can able to go for the roller, and then to measure the thickness, we can use the laser or any kind of laser measurement system to check the uniform thickness, whether it is coming or not. Dia, that means die of the filament. Then we can able to wind in the spooler. So after winding, we can take it to the things. So like this, the continuous process can be happen the things. So what is the advantage and disadvantage of single screw as well as double screw? Means as I discussed initially, so single screw is it's a low cost, mechanically simplicity, low maintenance. The problem is here poor mixing. The material cannot be mixing properly and not suitable for high heat sensitive materials. But advantage is there, low shear and no vent, good for the shear sensitive of polymer and additives. When we are going for the twin screw extrusion, here we can able to go for the high dispersion capacity, resulting in better mixing, better control of process parameter, easy material feeding, and high productivity and flexibility. And same thing for vent is present. And the problem is high cost. The printer high cost. If you want to go to procure for example, a filament extruder from the Thermo Fisher, the cost will be more than 1.5 crore is there. So if you are going for the only single screw extruder, the cost may be reduced to things. So like this, many high cost equipment is required and a high input energy, not suitable for shear sensitive materials. So but however, for mixing will be good. We can able to get the more composite based material. We can prefer the twin screw extruder. After otherwise, if you are getting the master batch, if you are getting the filament is uniform after mixing, then we can able to go for the even single screw extruder for making the composite filament also well and good. So both the things we can able to decide. So what is happening in the screw rotation of the either counter rotation or co-rotation. So this is the counter rotation of the imaging. This is the co-rotation of the images. So both is, if in case of co-rotation of the images, we can't able to get the uniform mixing of the things. When we are going for the counter rotating, we can able to get the good one. Compared to co-rotating system, the counter rotating system is more useful for the dispersing the fillers in the polymer matrix because it produces high shear forces when the materials are sequestered in the gaps between the screws. So that's why it's a counter rotating. We can able to get the proper mixing the things, because that means when you are adding the fillers with the polymer, it will be mixed uniformly and we can able to get the uniformly distribute the filament. So in case of co-rotating, that is the issue, the things. So based on that, we can decide which kind of rotation we need. The twin screw is record the things. The twin screw extruder is more efficient to mix two or more material homogeneously and widely used to make the polymer composite filaments, the things. So in this case, also three things will be there. One will be the feed, transition, and metering. And feed section, we have to feed the material, and melt section, the material will be melted and it form just like a flowable liquid. Then metering pump system will be a flowable liquid throughout through dye. The material will be come out with just like a viscous fluid. So once the viscous fluid coming out, we have to use the either water bath in the form of hot or cold or air. Then it will be cooled down and we can able to get the printed filaments. So what are the materials we can able to get? What is the advantagements? That material can be any application we can decide, either electronic material, composite material, biomaterial, ceramic, smart, and mainly application means that means semi-crystalline material also we can able to use, and amorphous material also is there. Commodity, engineering, high performance. So that is depends upon the high printing temperature, performance, and cost will be vary the things. So normally people will use the PLA and ABS is the commodity materials. Most of the printers will come with the PLA and ABC, these two materials. Still, if I want to go for the next level of the materials, people will prefer the PC as well as TPU, as well as a polyamide 12 nylon based material. Still, I want to go for the biomaterials or high temperature materials, mechanical stable material. We can go for the PA or peak materials. So based on the application, we have to decide which kind of material, which material we have to decide. Accordingly, the printer. If some printer cannot be printer, because low cost printer, we can't go for the peak or PA materials because it's record the high temperature. So that's why we have to decide based on the temperature, based on the printer, we can decide which material can possible to go forward, which can able to print the things. So these are the various materials. All the materials having the advantages and disadvantages. Depends upon the application, we can decide which kind of material is required for the things. For example, polylactic acid, if you are taking the things, it's a user-friendly and low temperature materials, but the problem of the thing is durability is less and heat resistance is not there, but strength and stiffness is good and chemical resistance also less. But however, it is a biodegradable, eco-friendly, low cost and biocompatible. So advantage is also is there. That's what many people are using for the polylactic acid. But mechanical, that means durability and heat resistance, chemical resistance issues there. So that's what some of the application is not suitable. We have to decide for the other materials, ABS. In this case, the compared to that heat resistant, it's almost all the cases it's coming under moderate. So strength, stiffness, durable, printable, and heat resistance. So the people may prefer by the compared to PLA, people will prefer by the ABS things, acrylonitrile butadiene sterile materials. So similarly, still we want to go for the next level of the things. We can go for the nylon based material. The temperature will be high, heat resistant, it's a chemical resistant, and durable is good. The printability is problem is less because it's a high temperature. Some printer cannot be print. So, but however, recent advanced printers we can able to print by using the nylon. Nylon is a flexible, durable plastic with less strength and stiffness than both PLA and ABS. It's most of the application, high temperature application of the chemically resistant things, we can able to go for the nylon. So similarly for polyether ether ketone, it's an excellent biocompatibility materials and it's a less wide, high mechanical properties and moisture also less. So this can be suitable for many applications. The PEEK is a colorless, semi-crystalline organic thermoplastic. PEEK is one of the widely used high performance polymers, and it's mostly using for the biomedical application. So the people will prefer for this PEEK material, the things. And what is the overall view of the strength, stiffness, durability means we can able to say PLA, nylon, or acrylic. Mostly people decide ABS things, ABS based materials, most of the applications. And this is the properties of the, as we know, everyone, we know the what is the glass tension temperature, melting temperature, all the things. But printing temperature mostly required for this material is for PLA means we have to go for the 190 to 220, and ABS little higher temperature 220 50, and nylon 270 we have to go, and PC and PEEK we have to go for the high temperature of around 350 450. So similarly, according to this temperature, we have to fix the bed temperature also a little bit lower than the printing temperature. Then we can able to attach the things with it. Attach the layer by layer attachment will be good. So that also bed temperature, PLA is less temperature. In case of PEEK, we have to go for the high temperature because of the high temperature of the PEEK materials. So this is the one of the methods what we have done in our lab itself. First, initially we have mixed. We want to make some kind of composite material, various applications starting with this electronic semiconductor application as well as the energy conversion and storage devices based system. We are fabricating various filaments by using these things. In this case, we are using the batch mixing process. With that, we are mixing the things. After making the clumps, then we can go. We are making into the this are nylon pellets, and then we added with the active material Al2O3, whatever the material, mix with the additives as well as a plasticizer. Then we can able to get the clumps. Then after grinding, we can able to get the small pellets. Those pellets can be printed using the filament extruder. These are the various filament with the various percentage. When we can use the ceramic fillers of 5%, 10%, 50%. If you are going above 40% or 50%, the filaments getting the brittle because of the ceramic conductor will be high, polymer conductor will be low. Then this is getting brittle and it is easily breakable, the things. So if you want to add the things more than 30% or 40%, we have to add the plasticizer. When we are adding the plasticizer, less percentage is no problem. That time also we can able to go for only 50% of fillers. Then still, if you want to add more amount of the fillers, the plasticizer, then when you are adding more plasticizer, it is coming like a flowable liquid. So that's what we have to optimize for the maximum things. When we can't able to go for the more than 40%, still many researchers is happening to increase the filler percentage. Then only we can able to go for the 100% utilization of the material for the particular application. Otherwise, filler based system, filler based application only we can use this kind of filament. Application. This is the one kind of things as I discussed initially. We can able to go for the master batch and then we can able to extrude the things. So these are the various filaments are the things. Nylon plus with the various percentage. These are the printed filaments. This filament dia, whatever we have printed, the dia is obviously it is coming 1.69 mm to 1.75 mm. And this is another one, ABS based filament. If for example, if you are going for the, that means initially when you are going still 50-50, the filament is going good. When you are increasing the percentage of the fillers, it is coming, it's not printing, filament is not coming uniformly. That is just like a small pieces only, it's coming out. So that's what we have to optimize the filler percentage with the plasticizer as well as the, whatever the editing you are using, or any other polymer, the things, processing temperature, processing parameter, we can able to get the things. And this is a one kind of filament extruder things. We have, apart from that, other applications we have fabricated for the some kind of energy storage devices application, also various lithium iron phosphate or graphite or lithium cobalt oxide, those kind of material also we have prepared the filament as well as they printed those filament. These are the filament, and for initially we have get the pellets, compounded pellets, then filament, then printed parts and coated with the current collectors. So this is a filament extruder setup. And then this filament extruder, this is the printer, and this is the printed parts. If you are seeing the things, sorry. So when we are, so this is the printing one, how the printer 3D printing is happening. This is our own filament, so it is printing is good. Similarly, in this case also, sorry. So this is one kind of filament extruder. Here you can see the things. So this is a feeding zone, and this is a nozzle. From this nozzle, the filament is coming out. This is based on the air based cooling. So air based cooling. So once it's cooling, the filament is coming out, and then here we can adjust the thickness by using this one. One of the system is using by using manual. So manual, and then it is strengthening and adjusting the dia, and finally it will be winded in the spooler. So like this, we can able to go for this low cost filament extruder. We are having another kind of filament extruder also. There we can able to print by using the thickness. The thickness will be measured by using the laser, and everything is good. There we can able to get the almost plus or minus 1%, less than 1% error based print. That means dia we can able to get the things. So after making this filament, next we have to go for next if those filament, the printed filament, that means fabricated filament only printed by using the filament extruder things. So these are the printed these are the fabricated filaments, that means battery based materials. So you can see the cross section we have checked with the XRD, FESM and EDAX based system, and also we have checked with the mechanical property. It's showing the through the filler has been spreaded inside the mixed with the polymer, as well as the strength of the filament also is good. With that only we have printed the things. You can see the things uniform distribution of the active material things. These are the some of the confirmation we have done to make the to confirm over the fabricated filament is good like this. So similarly for these are the things where the fabricated filament has been used for the various application of the things. So mainly for people who have started using for the healthcare application, aerospace application, or any other that means educational purpose also. Apart from that, energy storage, energy conversion also is application. Many researchers are also working for the energy storage application, battery or capacitor based things. The similar method what we have prepared, like that only other researchers also fabricated. That means they have made the ball milling process, they have made the powder, and then they have made into the pellet, and those pellets can be input into the extruder. They got the printed the things. So these are the various printed parts, the three-dimensional parts for the using for the battery application. And this is another things also they have made for the integrated things. That means they have made it a TPU, was LFP based LFP and TPU, LTO and TPU graphite and TPU NCM based various battery material and filament has been fabricated. Those things can be printed with a different structure and different dimensions and interdigitated pattern or stacking of the layer. So like this, many design they have printed, and those can be tested with the things. And you can see about the very flexible things, and that can be attached to the anode and cathode or electrode, or either way, either attaching with the electrode or calendering by process also is possible, or we can able to go for the coating with the thermal evaporation or sputtering. We can directly coat over the freestanding film, then we can make a device that can be used for the energy storage application. The problem of this kind of application is that this kind of material for here means the polymer content will be high, active material is low, so automatically the performance will be less. So that's why we have to play with the still. We need to reduce the polymer content. We have to increase the active materials. And this is the another materials, small chip based things also we can able to do prepared. And this is the tested with the material. The performance is showing good compared to the it's comparable with the other fabricated method also. So similarly for FDM based printed for the supercapacitor also application, also various printing application, various ink based system also ink have prepared filament, those things, carbon based materials, many materials is possible. So those things also fabricated. Then apart from that, energy harvesting application also we can able to use for making the 3D printed energy harvesting, either piezoelectric application or triboelectric application. We can use for the friction based system, or we can able to use for the compression, that means mechanical energy converted into electrical energy. So like this, various structures we can able to go forward, we can able to prepare, and that can be implemented for the energy harvesting and producing the energy by using waste mechanical energy into electrical energy. So as I discussed things, many application we can able to use for this 3D printing FDM based system. So the problem of FDM based system is the problem is supporting only few thermoplastic materials, and melting point of the incorporated medicine record to be near or higher melting point of things, and resolution of the things, because once the resolution, if the thickness of the things varying, automatically the surface finish will not be good. So that's what we have to go for the highly resolution based things. And when we are adding the more filler of the things, the filament getting brittle and we can't able to print the things. So many problem is there. Although the problem is there, still advantage of this is its high manufacturing speed, efficiency is good, and it on-demand preparation is possible, and personalized device also is possible in this case. So overall, compared to other technique, this technique is good, because although the cost, the many issues are there, the cost will be less, and it is processability speed is high. So that's what it is. Economic, less cost, we can go. Automated manufacturing is possible, and speed is good. The problem is only large production cost and limited strength when compared to the other technique, the things. So that's finally my summary is the FDM based printer has become the most accessible and widely used additive manufacturing technology due to its low cost, material variety, and user friendliness, saving industry and educators. While lack of precision of while compared to SLA and SS, the precision will be high. However, it dominates the rapid prototyping and functionalization and customization where affordability matter. And also, it's possible for the high material performances, multi-material printing, ASD printing, where the expanding in use of the aerospace, automatic, and medical fields, overcoming past limitation like surface quality. And future growth lies in sustainable materials, large-scale production, and hybrid techniques, ensuring in role in on-demand and distributing manufacturing. Though SLA and SLS may suit high precision needs, FDM and FFF remains unmatched in versatility and cost efficiency, and secure in place both consumer as well as the 3D printing for industrial 3D printing for the foreseeable future. So like that, many advantages also is there, although it has the disadvantage of FDM based system. In future, in every home, we can have the one FDM based system, because it's a cost effective. We can replace our parts, whatever the damaged parts in our home, easily with the 3D printers using the whatever the design is available. So thank you. And thanks, acknowledge my various funding agency to supports various R&D activities. Thanks, madam. Thank you to all.
Thank you, sir. Thank you for sharing a very valuable knowledge with us. So, in between that, due to technical issue, there is some problems. Sorry for the inconvenience caused. So, dear participants, if you're having any questions, please unmute your mic and then ask your questions. Any questions, sir?
Hello, sir. Good evening, sir.
Yes, good evening.
Yes, sir, please.
This is Vijayan from Satyabama University, sir.
Yes, sir.
Currently, my students done this FDM. They added some fillers, natural fillers, in that ABS material and extrusion process. They face
Yes,
the
sir.
problem that after extrusion, some
Yeah.
machines are not supporting that when natural fillers are added in a filament. it is not supporting like that. Is it? We have to
So
take any
what is
other
the
test?
percentage they have used, sir, fillers?
Less than 1%, sir.
So the filler
They,
size will be particle size is lesser, na? It's not a bigger one, na?
no, sir. In that time, when extrusion or printing, in that time, the distraction that is not properly coated like that. They tell.
That means the fillers is not uniformly distributed, or whether you have checked with whether the uniform distribution is there fillers.
No, that's not.
Yeah,
So we
we have to
have
check.
to check
We have to,
the.
we have to check the MFI value, because the commercial printer, we know the MFI. This is the MFI record for the printing of the things. Melt flow value, melt flow index, the things. Similarly, the same kind of MFI value we have to achieve the things with the order after adding the fillers, at least nearly. Otherwise, based on the flow, we have to change the printing parameters, whether temperature or the temperature has to be changed. Then the flow of the red molten state will be vary. Then we can able to print. It should not be stuck in the nozzle. Please check with the once again nozzle, if the nozzle anything is stuck or not. If there is no stuck, it has to come. The fillers, surely it will come.
Okay.
So,
Yeah, that is
some of the printer, if they have blocked with the blocked, then we can't able to do the things. So now open source printer is there. In open source printer, we can able to use any material, but we have to make the realizable property. They should be matched with the commercial filament. Then only we can able to print. And the size should be uniform. The printer, the filament size throughout the filament. If it is, the size is varying, then in the nozzle, it will not come out. That problem also is there.
It depend on material extrusion machine.
Yes.
Sure. Okay. Thank you.
Sir, there is one question in the chat box, sir, from Vinod Kumar,
Yes.
sir. So, what will be the cost of the filament extrusion machine price, sir? He's asking the
Sir,
machine
if
price.
you are going in Indian machine, less than 10 lakh is available, sir. Small machine, lab scale. If you are going for the high-end machine, you have to spend for at least 1 crore. You can able to get the gooder one, either German one or UK one.
Yeah, fine.
What we have procured, almost it's 1.7 crore.
Yeah, gosh.
Yes, sir.
Any other questions, sir, from participants side? Sir, one more question from my side. So, what about
Yes,
the
sir.
filament cost, sir? If you're by using a fiber filaments, composite, glass fiber, or any other carbon fiber, in that I need to incorporate any nanoparticles like graphite nanoparticles or carbon nanoparticles. Means, what about the filament cost, sir? Comparatively from the traditional one, it will be higher or lesser, sir?
Sir, it will be higher, sir, because you are going for a particular application, na.
Yes,
You are
sir.
adding fillers. So it is not much higher. Based on the percentage of fillers and the printable property, little higher only. It's not much higher.
Okay.
Yes,
Similarly, we can fabricate the 3D printed composite in various orientations, sir. Is it possible from the 3D printing?
Yes, orientation. Various orientation is possible. Yes,
Okay,
sir.
sir. Okay, sir. So we can get the fabrication from your institute, sir. Is there any possibilities?
Yeah, it is. It's possible. It is possible. Yes, sir.
Okay, sir. Okay, thank you, sir.
Yes,
okay. Any other questions from participants side? Okay, sir. There is no questions, I hope. So thank you, sir. Thank you so much for a valuable sharing valuable knowledge, and also you spend more than 2 hours time with us. Thank you, sir. Thank you so much.
Thank you, sir. Thank you for your invitation. Thank you, sir. Yeah.
Thank you, sir.